All right, so I'll travel back to time when I first met Alan. That was when he was a Maury assistant professor at UC Berkeley. I started my PhD journey in the early 90s. And we had weekly LEPAC group meetings, if you remember. If you look at the list of people, so there are 4 professors, 3 students, and if the students were outnumbered by professors, you can picture in your mind what's it like in the meeting. So, so the first semester, most of us, 3 of us, we were, in most of the meetings, we were pretty speechless. We didn't quite follow what these 4 were talking about. So almost after every meeting, we have to have well, especially me, I had to get some private session with Alan, ask him a lot of questions about what happened at the meeting. But the biggest thing I learned from the meeting is SVD is a big thing. And actually, it's quite useful in the talk I'm doing today. And another thing is we get reinforcement learning yesterday from Gil's lecture about SVD. It's 2 by 2. That's wonderful. All right, so let's start with something very universal. One of the universals in linear algebra. It's solve a dense algebraic system. Could be a linear system eigenvalue problem. And our commonly used, the most widely used tools, LU decomposition, Cholesky decomposition, QR, blah, 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 SVD, for the eigenvalue singular value problem. And obviously you hit the complexity wall, you cannot go over that. It's n cube and n square memory. It's not so great. So what I'm going to talk about is some ways to lower the complexity. They are not unique, there are many ways. So for example, like yesterday, Dan gave a very nice talk about another way of doing this. So what we're doing is mainly focus on the off-diagonal low rank representation. And there are quite a few, more than 10, I would say. And one of the tools we use to find all these bases is randomized algorithms. So it could be sketching, or geometrically you could say approximate the nearest neighbor, etc. So today I'm going to focus mostly on the algebraic. So for the matrix, for any matrix, the global matrix is not, it's never, very rarely it's low rank. But the off-diagonal blocks, they are low rank. You can think about that's the foundation, mathematical foundation of fast multiple algorithm, right? So you do the particles, when they are close together, you just do resolution higher. But far away, you just lump them together to approximate. It's the same idea. So the diagonal is like your local particle, and off diagonal is far away particles. You do some approximation. And this field actually started, was invented many years ago by Hagebusch from Germany. He and his group. But it hasn't been too very widely, theoretically it's very well developed, but in terms of practical use, it's not widely used. It's just because there was not so much software. So nowadays you can see a lot of software, even David Key's group, they also have software. And in the algebraic way, compared to FMM, is that in algebraic way, you actually have more power. You can do matrix factorization, you can do inversion. So this is something FMM cannot do. But it's a little more technical. I'm not going to go into detail today. But the consequence of this is that you could get a direct solver, which is n to the alpha polylog n. And this alpha, depending on what kind of format and what's the rank, etc., could be as low as 1. But it's certainly smaller than 2. So that's a very good news. All right, so let's take a look at the sketching, randomized sketching. And this one is actually very popular. A lot of people already know about this. So you want to find the approximate range of matrix A. So what you do is you do suppose you know that your target is K. Obviously, in practice, you don't know the target. So that's some technical thing we have to deal with. We usually do adaptive sampling. But let's say you know the target is K, then you only need to pick K plus P some columns. And very often people just take omega to be, each entry is from a uniform normal distribution, 0, 1 normal distribution. And then after this sampling, this sketching, you get a Tolskini matrix. For this matrix, you find the orthogonal basis. And then you can actually show that it's well known, it's established that this projected matrix, you get a very good range, approximate A. So this approximation is very good. And in fact, you can have two kinds of bound. One is expected approximation, and another one is a probabilistic. With high probability, you have a successful bounded by this. Compared to SVD, the best rank K approximation, the best error is sigma K plus 1. But here, obviously, intuitively, you get some amplified factor. This factor related to matrix dimension and KP, etc. So that's pretty nice. And then we use this to do some application. So one of the applications I want to talk about is the kernel ridge regression. Nowadays, machine learning to do binary classification. And the relatively easier hierarchical format is this HSS format, hierarchical semi-separable. And you can see from the picture, it's more regular compared to the previous picture. You can have compression anywhere. It's harder to manage in reality. So this HSS is divide and conquer. It's starting from the top. You partition the matrix into two diagonal block, and then for each diagonal block, you continue to do the partition. So you always look at the diagonal block as your reference. And then you can get this representation, this is called a HSS tree. It's naturally coming from this recursive partition. So it's this one is basically the interval of the indices at each level. And so then how do you do the sketching? So basically what we do is we use omega matrix to sketch the whole matrix. That's the pre-processing step. But of course, we have all these little bases in the middle, right? We don't need a diagonal. So the trick here is that while you are at each level of this HS tree, you just subtract what you previously sketched of the diagonal part, but follow this the tree. So that's you get the actual sketching of each of these individual block here. Let me see what.
Jerry, are you assuming the blocks have a nested column?
Yes, this has a nested. So for example, that's a good question. That's the point of this HSS and H2. So this basis is actually, why is it short? Because you are not compressing from scratch. You're just, it's a combination of these two from the lower level. That's the nested part. Thank you for the question. All right, so let's take a look at this kernel ridge regression. It's very widely used to do it's a supervised learning mechanism, very widely used to do the classification. It could be binary, could be multicast. And there are two parts. One is regression. We are very familiar with the regression in this audience. Basically, you have your known data set xi, and since you know this and you know the y, these are the labels. And then you want to minimize the error. And with this W vector, but W is a vector normal to the target hyperplane to separate things. So this W is actually just your model parameter. It's in any machine learning model, you need to determine parameter. In this particular case, it's this W. But in the case of a neural network, it's this A, B matrices at each level that yesterday, Gil's lecture, he showed those A, B matrices. So this is our model parameters. And it can be computed by this, okay? This is your data matrix. So that's the training part. You want to get the best W fitting this as best as possible. Then the prediction part is, again, you take this model parameter, multiply with dot product with your new vector. You want to see which class is this finally. And again, matrix inversion problem. And people use the kernel trick. It's just that instead of directly doing this, they map into this kernel matrix so that you have easier. It's actually usually it's projection into the higher dimensional space. So it has get an easier separation. So that's just the kernel trick. But still, you have this inversion problem. So in the end, the classification is really just the label predicted by the sign of this. You don't need many digits, it's just the sign. So that's give you a hint that you can do approximation, right? So that's what we do. We compare with a lot of people use this scikit-learn. Unfortunately, it's Python, it's not Julia yet. So they use this to do a lot of things, classification, training different models, etc. And then we compare with using our scheme, this HSS scheme. This is in our paper a couple of years ago. And scikit-learn only has a shared memory parallelism. So here I'm doing a data set, SUSY, from this very popular, from University of California, Irvine, yeah. So on the x-axis, we are increasing the training set, the x data set. Y-axis is the fitting time doing this regression. So there are three curves. One is the scikit-learn, this origin one, and they only have shared memory parallelism. So it up to this size, then it couldn't do anymore. It out of memory, out of machine size. And then we have shared memory up to, in the beginning, it's slower. It's pretty complicated algorithm, so you have a bigger prefactor, even though it's a lower complexity. But when your problem size increasing, you can see it's almost tracking like a linear time, linear polylog n. So this is a distributed, this black one is a distributed MPI code. And so we have scikit-learn, the interface, so people can use, our classes are built on the, using the scikit-learn, derived from scikit-learn, so people can use this to access all the scikit-learn capability, but with a faster LU, Cholesky factorization, faster than Cholesky in scikit-learn. All right, so I'm going to spend about 10 minutes talking about, can we do even faster? Okay, so here, the bottleneck here is the sketching. You can see that if you take omega matrix dense, right, it's still order MMP. And what we're going to achieve here is doing something like in this framework called the Johnson-Lindenstrauss sketching framework. It's not a single algorithm, it's the whole family of algorithms, a lot of them. But the fundamental mathematics is this based on this JL lemma. It just says that if you have a set P of n points in an n-dimensional space, and with it D bigger than some this mysterious number, log m, then there exists a mapping. Usually this map is a linear map, which does the dimension reduction. So it reduces your dimension from n to D, okay? And then it preserves the difference between the 2 points after the mapping in the lower dimension is preserved. So that's the JL lemma. And then the JL sketching operator it's really coming from the distribution of this D is a distribution over the matrix of size D times n. So we take one matrix R in this D distribution with these kind of parameters. And then you see that this, it shows it's a single vector length is preserved if you have this property. So if you satisfy this property, then it's considered JL sketching operator. So it's a family of things, it's just not just one. So that's the property you need to satisfy. And then the Woodruff proved that this is single vector case. Then when you talk about multiple vector, then this actually has a very good subspace embedding. Okay, so the experiment, the result I'm going to show you is the sparse version of JLT. So there's quite a bit mathematical thing here. So a mouthful of things. But essentially it says that suppose you have a D by N matrix, then for each column, I only choose alpha non-zeros. And this could be random location. Between the columns, they are independent. And the value of this is follow this Rademacher distribution. So it's scaled. So it's taking value, it's 50-50 probability. All right. So we use, from dimension point of view, we usually use the notation transpose because that's the dimension matching our sketching. So if you write this R, it's actually, you can just split into two parts. B plus, I call B plus B minus, they're binary. B are just binary. So then you can do multiplication. There's really no multiplication. It's just addition. No multiplication is involved. And then you use a sparse representation for each of these guys, the CSR or CSE, and without the value, just the indices, because there is one negative or 1 here. So it's implementation, it's actually easier than any SPMV. Okay, so that's the basic idea. So I'll mention two theorem which is useful, especially the second one is in practice. The first one, you want to show that the quality of this range approximation is good. So this kind of thing you already saw in earlier, a few slides back. That's for Gaussian matrix. You have, sorry, I missed A here. So you have this residual, it's bounded by this projection operator by certain constant times sigma R plus 1. Okay, it's not going to be as good as SVD, but with some constant, hopefully tolerable. So the theorem in our paper is this. So what I'm going to say is that first of all, you have to, after you do all the derivation, you have this mysterious numbers, the parameters associated with the original sigma delta. And then with high probability, you will succeed with this range approximation is as good, it's almost, not too bad. Another one in practice, it's very useful is, as I mentioned, we have to do incremental sampling because you don't know K, you don't know R basically for each block or anything. So you do this adaptive, it's not a big deal. The trouble is, mathematically is not a big deal, is how do you stop? And in the case of sketching, we actually, in the application, we don't have matrix A. We cannot, we don't know, but we only have the sketched matrix, which is this guy. So we have shown that this Frobenius norm has a good relation with the original matrix A. So when you do the incremental sketching, the error, you can have a good control with your current sketched sample. So that's the general idea. But of course, it's pretty deep when you do the derivation. So we did this in the uniform framework, both for Gaussian SRHT and sparse JLT, and then derived D has to be, this basically say D has to be of certain size to be able to say good accurate result. So that's this two theory. So I will show just two practical side. One is the accuracy, and another one is the speed. All right. So for accuracy, we have done quite a few problems, but here I'll just show you one. And we compared with Gaussian sketching, this SJLT. And there are two rows of the picture. The first row is the relative error of this approximate H compared to A. And the second row is the HSS rank, the off-diagonal rank. So you can see that for this matrix, when I increase the problem size, and also the different color is a different compression tolerance for HSS. So we start with loose, very loose approximation, and the middle one is 10 to the 4. The blue one is 10 to the minus 6. So if you look at the first column is Gaussian, and then it's S with only one non-zero per column. And S2 is 2, and S8 is 8 non-zero per column. So you see that S1 is not so good. S2, sometimes it's not so good either in terms of accuracy. But S4, even just 4 non-zero per column, it's good enough. So you can see all these S4 is good enough. And then you can see the rank with higher, it's expected with a higher tolerance, with more compression, then your rank is bigger. So it can be several hundred for the 3D Poisson. So it's not a very small. And then what about the speed? So the speed here is we again compare with the Gaussian. Then we have two matrices. So one is from integral formulation of scattering wave equation, and another one is from 3D Poisson, the one I showed just the previous slide. So lower is better. But you can see that the sketch is actually quite expensive, I mentioned. In this, the total compression time for Gaussian, majority of the time is in sketching. And then when you use this SGLT, the sketching time could be lowered. And in general, for a lot of other matrices, we have seen up to 2.5x speed up. All right, so this is the software we have in StrongPack. And hopefully by the end of summer, we'll have a Julia interface to StrongPack. It's a distributed memory. A lot of these options are there, the structured matrix, many formats. And one last thing I want to show is actually Ray Chimera. He's a student of Alan, and he's doing the summer intern. Oh, there, Ray. You should do a wave. Yeah. Thank you for the hard work. So in the summer, he finished, almost finished. Right now, it's almost ready to use. The interface to distributed Super LU, it's a different code. It's a direct solver, no compression, no approximation. And you can see that this is the MPI. It works on multiple nodes, MPI. So the Julia code is very simple, MPI init. And then you say, this is process grid. And here we only need to use a 32-bit integer. I still didn't know why yesterday we need to use a 64-bit integer. And then you just say, A is a distributed supermatrix, which is internally in the Super LU some structure. But from user point of view, it's really carefree, right? And then load the matrix here. So one quiz, and then it's similar like a MATLAB backslash we like. So, oh yeah, so F, yeah. Yeah, that's a factor. It's a factor, yeah. So one quiz I want to leave with you is, what the hell is this exclamation here? I know now, but when I first saw the Julia code, I'm completely puzzled. Can someone...
You have to be a Steam programmer to know the answer.
Can someone not from Julia community answer this question?
It's shouting it. Really fluent. This is LU.
This is LU, yeah.
Should the answer be at the very first line of JuliaLang.org?
So the answer, let me see, that's my understanding, whether it's correct, Ray, tell me. The answer is if the argument, they want to emphasize if the argument is modified. So if everything is input, then you don't need, I mean, they don't do this, but if the argument is after return, A is modified in this case. So then they give you a hint.
That's what they say, it's factorial.
It's, oh, okay. It's not exclamation, it's factorial. All right. Thank you so much, and happy birthday.
Are there any questions? No questions?
Okay.
Then let's thank Sherry again.
Thank you.